Yo, what's cracking YouTube? Welcome back to KrossDline, simple development log for my machine learning research project. If you're interested in conducting some of your own research but don't know where to start or what neural networks and AI are all about, you're in the right place. Just check out my previous videos to cover motivations and scope of the project if you're unfamiliar with this work, because this isn't the first rendition or episode, obviously. So check out the channel for more details and my motivations and latent biases and the approach I'm going to be taking to this the whole way. As I mentioned in my other videos at great length, the intention of keeping a video log for this project's progression is as much a learning resource as it is tracking progress for myself. It's sort of version control for like my reasoning or my judgments, just in case, or not in case, but when they inevitably fail me, I'll be able to, track myself back and figure out where my flaws were or where the errors were in my reasoning, basically. So I'm almost done covering some of the groundwork for this project. I've been sort of laying a baseline, trying to just establish the starting position for the work that we're going forward with, and the spirit and the intention of the project, and my affinities for like open source tools, and the approach I'm going to be taking, like by training and processing neural networks through 3D engines or game engines and things like that, to help visualize the data as opposed to simply just doing everything in code and writing mathematical formulas and then expecting everything to just sort of make intuitive sense to people who aren't as literate in Greek like I am. Saying that I'm not literate in Greek, that is. So I covered some code, some theory, some of my expectations and biases, as I said, and I laid a bit of groundwork for the angle of attack that I plan to be going about my business here, but this sort of still leaves us with checking in on some of the fundamentals of math. And like most researchers and academics can justly assume that a certain baseline of competence in math pre-exists, and they can kind of just go about their videos describing things using the technical terms and jargon. But unlike most videos, I'm not coming from an academic background, and most data scientists, I think, on YouTube have fantastic resources for this type of thing. I'm not at all trying to say that there's no value in that, but my approach is going to be more making things intuitive and legible to the layman, basically. And I'm only going to be using those technical terms when they're absolutely necessary, just for the sake of understanding the fundamental principles of the work that I'm doing. Because like the way I see it is if you already learn how to drive a standard transmission automobile and you don't know any of the words for any of the parts of the cars, it's much easier to then give you the word like clutch after the fact when you know how to use the clutch, to remember then what it's for and what it does and all that. Much the same as if you're learning auto mechanics. If you already know how to drive a car and you have some kind of familiarity with the mechanics and like how things move and interact with each other and the dynamics of the system that you're operating in, it's much easier then to get an understanding of the technical engineering that went underneath it. So with my approach, instead of learning the math and the calculus first and then building neural networks off of that, I'm sort of going to be trying to discover an intuitive understanding of the calculus behind neural networks and AI in my research project first, like understanding the dynamics of how the thing works and putting it together, and like I said, my angle of approach and all that, and then sort of tying the math into it underneath. But to do that, there's still going to be some baseline of math we need to understand. And that's because a lot of what we're doing in math is going to be like operating with matrices, and because I'm using a 3D engine, all of that works with vertices and vectors and different spaces, like color space versus like 3D space, and then a timeline would be a separate dimension, so we have to understand some type of concept of dimensionality and encoding and embedding data inside of those dimensions and then sort of passing them forward or bringing them back. That way we can get a grasp of ideas and principles and concepts like convolutions, recurrence, recursion, and that kind of thing. So, as I said, I'm going to be covering some code, but again, it's not like this is a programming tutorial, or like those other videos were programming tutorials. I'm going to be covering some theory, but again, this is not like a data science or statistics like open course or something. It really is a development log, but for these first few videos, I'm laying the groundwork just so that we have some sort of baseline that we can all assume an understanding of. So if you're already familiar with this, that's great. It's basically just a refresher, but if you're not completely familiar with this already, it'll give you some kind of checklist to know what you might want to look into a little bit more before moving forward, or at least if you move forward and you get stuck, then you know perhaps what it is that you need to look into to hurdle the hurdles, basically. So it's kind of important to get the language of math under your belt just a little bit so that it doesn't become a hiccup every time I need to look something up, or so that I can even ask a competent or coherent question if I do get stumbled or tripped up somewhere. To have the language to know how to ask for the thing that I don't know requires, again, some kind of baseline understanding. So knowing how to speak the language of data science and statistics is kind of important in that regard. And it's definitely valuable to know all the specifics, but that you'd probably get a better understanding from, like I said, other videos by like instructors and professors and teachers and things. This is not going to be that. So I'm going to just cover the math we need for the project only today. Just to get started, so that I'm not assuming that anybody has an understanding of things that I didn't have when I started. So I had to go back into high school maths and just did some catch-up course. So this is just going to be some of those concepts that I use from that high school math catch-up course I had to take, just to get the ball rolling and everything on this project. So yeah, I'll consider it more like a documented record for the reasons I make mistakes, which I'm bound to make, but documenting my proficiency might also help save some time in dissecting my errors when I do look for help, because then it'll give somebody else who's more knowledgeable a better idea of where I might be lacking and where I might be tripping myself up. So whatever, things like that. So while some are going to find these examples and analogies useful, I guess, for their establishing their own baselines, others are going to find it pretty pedestrian, and maybe this video for them might be worth skipping. I don't know. But for me, it's definitely going to be useful because I'm going to have to check back on it because, as I said, I don't really have a firm grasp of all the mathematical concepts or specific terms myself. I've just sort of been playing with neural networks for a few years here, and I've got some ideas that I wanted to test out, and figured I'd document the process along the way in case anybody else wanted to either help with this project or wanted to start their own project and use some of the ideas or concepts that I bring up here. Or maybe like me, they have difficulty in learning math the traditional way, and maybe this type of applied math might be an easier way for them to get into the academic fields or STEM studies, or even just to realize if they're interested. It's hopefully to be less dry than just doing equations and learning rules and memorizing formulae. But yeah, a big reason to understand at least a baseline, though, is just to be able to articulate the things you do and don't know, and to convey ideas without stumbling unnecessarily on language, because it sort of makes it hard to communicate when you don't have the words to do so. But other than that, yeah, so I guess I'll just get right to it. I guess we'll start it with charts and graphs. So a graph is not a chart. That's the first thing. And a lot of people misinterpret these, or they conflate the two concepts together. And coming from a financial background as I did, I sort of learned my math and statistics by watching financial markets. And that to me was much easier than going through textbooks and learning like weighted averages and means and things and norms and things like that just by memorizing definitions and doing question and answers. Following markets sort of makes it not just more visual because you use charts a lot in financial analysis, but it makes it practical too. You see which things are useful in which ways and how they respond dynamically, because obviously prices are updated on a per tick basis. So that helped me a lot. But charts and graphs are very different. So let's start off with charts versus graphs. Okay, so this is a chart. Okay. This is a graph. When you have this relationship to here, this relationship to here, this relationship to here, maybe this goes here, or however you want to have this structured, right? Doesn't really matter. The point is, a graph is like a node structure that defines relationships between things, and these are very useful and can be run as neural networks, but they're a completely different type of structure of neural network because of the emphasis on the relationships between hierarchies and connections. So one example of when a graph might be useful is if you're doing the traveling salesman problem. Like, let's say you had a salesman in a state or a province or a country or something, and they had to visit every city, but you wanted to find the best path to all the cities. You might use a graph, because then you could take the length, like say this is 7 kilometers, this is 3 kilometers, this is 1 kilometer, etc. And then you might just like measure all the connections and try to not pass through the same one twice, because if you only need to visit every city once, you'd be wasting time going back and forth through all of them. And this is a notoriously difficult problem because as the number of cities grows, the complexity of the problem scales exponentially, because all of the possible paths you can take with every one node that you add adds a factor that compounds upon the previous number of different paths you could have taken to achieve your goal. So if you're looking to get the shortest path, you'd probably go through a graph structure, because charting out a city and its distance from your starting point wouldn't really be helpful, because every different city is going to be relative to the previous point. So let's say if you started here and you move down here, it doesn't really help you to know how far this node is from your starting point, because once you're here, you're going to want to know the path to all your other areas. So you might go up this way and then down this way and then up this way across like that. You know what I mean? And that's not going to do you any good having it charted out on here. Like if you had distance over here and then cities down here, right, in a traditional chart. So that's what graphs are for, is for relationships between different nodes of objects or subjects or hierarchies, things like that. Like you think of the file structure in your computer, you might have like your desktop up here, and then you've got like pictures and music or something like that, right? Knowing the file path or structure to your file system, I'll call this FS. Still learning how to use these pens. And inside music, you might have like different artists, and inside different artists, you might have different albums. And then inside each of those albums, you might have like re-releases. Anyway, you get the idea. See, these are hierarchical relationships, and they can sort of backtrack through a path of connections, but this node doesn't really connect to your pictures folder, right? Whereas charts are very useful if you had things like you were tracking prices. So if I had a graph that went this way and let's say you had a price action that goes like this on a stock. You might want to know like what your lowest is, so you might track on the chart some highs and lows to find yourself a range. You might look for a standard deviation of bands, so that would be like a Bollinger Band here to spot breakouts or ranges if you're an intraday range trader. You might want to know what the moving average is, so that might be a line that goes through like this, so that you can see a downward trend sort of establish itself once it crosses a moving average through the price line. Or you might have different timelines of moving averages. So one that lasts like 200 days might be a lot smoother than one that only lasts 40 days, because the stochasticity of a 40-day average is going to be much higher than the stochasticity of like a 200-day simple moving average. So then you might use the signal from a 200-day moving average crossing, or I mean a 40-day moving average or a 50-day moving average crossing a 200-day moving average to signal to yourself, hey, this price action is determining a trend reversal or something along those regards. So fundamentally, charts and graphs do completely different things. Even though they're both pictorial representations of data, they're definitely not the same thing. So that's one key important thing to note. Charts and graphs are different. I'm going to be using lots of charts, and if my first attempt at my neural network doesn't succeed, I'm probably going to have to build it out into a graph neural network, because essentially what I'm going to be doing is building separate models that do a bunch of small compartmentalized things, like small component models, and then compositing those component models together. So I'll use charts for the data analytics to build the models, and then once I have a whole bunch of models, like one that does language, one that does, edge detection in signal processing and audio, edge detection in images, color space representations. Like usually when you have a nice looking picture, there are colors that relate to each other and others that don't. So that'll be like themes for websites. You know, you can see a website that's really jarring when you look at it and the colors just don't match together. There are numerical values for those colors, and you can represent those relationships between the numerical values for the colors used in a theme on a website and determine whether one is more appealing than the other. You can have a neural network essentially analyze those types of relationships mathematically between the color spaces on a given design, for example, right? You could use neural networks on market data, like for price analytics and for signaling trend reversals or intraday ranges that you want to trade if you're scalping highs and lows, that kind of thing. But once you've got all these small models built up, you could have an audio processing model, a language model, an interpretation model, and yada, yada, yada. My idea is I'll probably need a graph neural network to then link all of those small models together to make a more comprehensive, artificial, generalizable, intelligent model. So my predominant model, the way that we're going about things these days with like GPT and supercomputers and everything, is they're basically trying to build one big model with like 100 billion parameters and use tons and tons of computing resources trying to build out one model that does everything, like the one model to rule them all. And my philosophy is the reason why Linux works better than Mac OS and Windows is because everything in Linux runs in small, compartmentalized, very precise units. And those programs do their designated functions, and they do them well, and that's all they do. And every time you need that function, you just call it, spits out its output, and then it ends its process if it needs to or whatever. So essentially, I want to build a neural network that's sort of structured in the same way that the Linux kernel and distributions and the Unix philosophy is centered around, having a whole bunch of really specific and tailored small neural networks, or I guess they don't even have to be neural networks. They can be any type of statistical inference model. But the point is, the graph network will be the one that would help me composite all of my small models, and my small models will probably use charts, data and statistical analysis to build themselves out and track their own cost functions and evaluate their efficacy, basically. So that's the main differences between graphs and charts. So the next thing we need to cover quickly is just vectors. So vectors are super important, and they sound daunting, but all they are is either a list in Python, as we've covered in some of our programming videos already, or it's an array in JavaScript. Could also be tuple. That's Python too. What else? I wouldn't consider an object necessarily. Like in JavaScript you have objects, but the equivalent is a dictionary. In Python, I wouldn't really consider those vectors because they're more like hash tables. And I think I'll probably cover that in a later video, because a hash table is just basically a reference table. So you've got, if you've got a person's name and their employee ID, and every time you have a database that looks at and says this employee ID has this schedule, if you ever wanted to see like, well, what, employee number 10256 means nothing to me. If I want to go speak to the person, I need to know like their name, their phone number, their address, and all that. A hash table would be the thing that you refer to check the ID and reference it to a person. And then when you check up the person, that person would have their own reference table of all of their properties. So like their name, their age, their social insurance number, and blah, blah, blah. So hash tables are really useful. They're along the lines of like linked lists and things like that, but that's more specific than we really need to get into until we start doing the the computing itself, the computation and the programming. So it's not really math related. But as far as vectors go, what we do need to know is that vectors are basically just lists, and they're listed in dimensionality. So this is a 1D list, or an array, in other words. Now you can have nested arrays. In programming, it would look something like this. Three, four, and you can think of it as like coordinate systems. So like if I wanted to draw a line on a coordinate space, I would need the start of the line, the starting point, x and y values, and the ending point, x and y values. That's a 2D list. It's a list of lists, or an array of arrays. It's this one big array with another array inside it and another array inside of it, right? So that would constitute a 2D array. And the thing that makes GPUs and specific hardware so effective for processing neural networks and AI is that we're going to be using very high dimensional lists. That's like embedded arrays, an array within an array, or a list within a list. They're all, what's the word for that? Synonymous. They're all synonymous, synonyms for vectors. And when you have a vector of vectors, you're basically just, at that point, vectors of vectors are matrices. So when Neo asks, what is the matrix? That's what it is. It's basically a vector of vector. But it doesn't have to be higher dimensional. It could be just a 2D vector with a lot more values in it, right? E, F, trying to remember my alphabet. So this is a matrix, and it's not necessarily a list of lists inside of it. It could just be a table of data, tabular data. And another way of putting this might be if I was talking about that person reference, right? So if this matrix is a person, I might have, let's say like names as one value, right? And then Chris, hold on, let me get some more room here. Chris, driver, And then on another row, I might have something else like age. And then that could be like, 30. And then it doesn't have anything in its other column. So I might put something like null, which is like a placeholder for no value exists. Something like that. This isn't how we'd structure it. I'm just sort of giving you an idea of like the purpose of a matrix as it is relative to a vector. So as we talked about with vector spaces, a list of lists would be something like the line where we needed a starting and ending point, and each of those 2 points would need a XY coordinate value. You want to keep those pieces of data completely contained together, because as soon as you swap the Y values of those 2 items, the whole line doesn't make sense anymore. Because you'd have the X coordinate for your starting position, but the Y coordinate for your finishing position, you'd get completely different lines drawn out from it. So you want to package those and keep them together, right? Whereas in this matrix, you might want to package them and keep them together, but you don't necessarily need to follow the same conventions of bundling them together. You can keep them as, you could take all of this So instead of having those coordinate spaces actually bundled together like that, you could manipulate them more if you had, say, like a 3D object. Not to be confused with 3D, the matrix style here, and I'll get into orders in just a second here. But a 3D object might have like an X, Y, R, G, B. So it might have an X coordinate, a Y coordinate, a red, green, and blue value for the pixel. So the dot isn't just a dot somewhere, it's a dot of a specific color. And that specific dot might be one line, one dimension of this 3D object having, say, 50 matrices. So this would be like X1, Y1, and this is a subscript I'm using here, whereas this would be an exponent, right? The superscript. So R1, and I'm tagging these with a subscript just to keep them in line so I know which point they pertain to, and oftentimes we'll just use an L for this, right? And if you're inside of a loop or an integral, and we'll get into that in a second when we start covering calculus and stuff, but this might be L1, L2, or L1, L1, L1. And then the next line here that it connects to would be the second value in that order function, right? RG, B, L, L, 2, 2, dot, 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 dot. Because this could be a really, really huge matrix. And we could have like, I don't know, 5,000 values in here. And all of these values together would describe this one 3D object, for example. And it makes more sense to bundle these in a matrix as opposed to bundling them, or it might make more sense to bundle them as a one giant matrix as opposed to bundling them together as like embedded matrices, right? Like this. This would be harder to process if I wanted to compare them with like collision detection or something, right? If I had 2 objects and I wanted to see if one crosses over into the other, well, at some point I'm going to have to start comparing like the edge structure of one object compared to the edge structure of another object. And as soon as I have nested values or nested arrays, I have to start iterating through loops of loops of loops, and that gets really big really fast. Whereas if I just have all of my object details bundled together in one matrix, I can compare this whole matrix to another object's full matrix and do all of those operations without the nested loops. And that removes a whole bunch of complexity with respect to from the perspective of like O notation. So big O notation is sort of a way of defining how an algorithm scales, basically. Or that's actually essentially exactly what it is. It's determining the scale of growth with every added component that you add into the algorithm, so that you get an idea of the processing time, or the maximum processing time it would take for this algorithm to run from start to finish. So matrices are super useful, very helpful, kind of confusing, so I'm just going to cover them quickly so that we know how to handle them and how to manage them. Okay, so first things first, order. These pens are really hard to work with. Matrices. Order. So when we're talking about the order, the reason that this is important to understand and know is because certain operations with matrices between each other require that the order actually be specifically congruent. Like, they have to line up with each other. Otherwise, it's not just that it's a rule, it's because it wouldn't actually make sense to perform the operation without them being equivalent, because then you'd have numbers that don't align, and they wouldn't have, you wouldn't be able to finish the function of the operation, right? It'll make more sense with an example, but it's gin o'clock. So generally speaking, we call these n by m. So what does that mean? If I have a matrix A, B, C, D, E, F, this is n, so that would be 2 in this case, and this is m, so that would be 1, 2, 3 in this case. So I would say the order of this matrix is an n, actually, I'll word it in English, n by m, and I would say it's a 2 by 3. And in order to run, like TensorFlow or PyTorch or any of the libraries that we're going to be using for machine learning, it matters that you know exactly what shape your network is, because the shape, because an invalid shape will mean your computer, your code will crash. You want to be able to run the training or the simulation or the input that you give it. They have to match the dimensionality or the order or the structure of the matrix that you're working with. So the only reason this is necessary, and the only reason you have to sort of know the terminology for this, is strictly speaking because the libraries we use to help us do our neural network training and evaluating our models and processing inputs, or even just conceptually thinking about how to go about creating a neural network, requires that you, before you do anything, before you even collect data or whatever, you have to understand the fact that there's going to be structure to this data, because you have to form and warp that structured data towards something that is going to be useful. You can't just dump anything at it and say, okay, you figure it out, because that's just not how computers work. They need to be told explicitly what to do. So to take advantage of the pre-built algorithms in like NumPy and in Python and in JavaScript or whatever programming language you decide to run your neural networks through, it requires that you have some basic knowledge of the inputs that they require. And that basically also means that you're going to have to reshape or transpose data sometimes. Can't get around it. So it's just a necessary thing to learn. Thankfully, that part's not, although it sounds confusing to sometimes, it's actually not as complicated as it sounds. Because it'll tell you exactly what's wrong when your code fails. It'll say, hey, your shape's wrong. And then you can just write a quick little script in your notepad that says, hey, tell me the shape of this, and then see why the shapes don't match. So, moving on, operations, I guess. I'll just quickly cover that. If you're doing operations on matrices, addition and subtraction are equivalent. So if you have, or even vectors, works the same way. If you have 1 and 2 plus 3 and 4, all you're doing is 1 plus 3, 2 plus 4. So that equals, what, 4 by 6? Look at me go, math course. So all you're doing is taking the top one to the bottom one. Simple enough. You're doing it with negatives, it would be the same thing, except it's like saying plus minus 3 plus minus 4, right? And then obviously you do the same outcome. 1 plus minus 3 is minus 2. 2 plus minus 4 is minus 2. Looks like a Z, but it's a 2. So addition, subtraction, very simple. I can't remember the word for it, commutative, associative, something like that. They can be put the other way around. So 3, 4 plus 1, 2 is the same thing. Well, I guess this would have to be minus, actually. You get the idea. Or I could say plus and say plus minus. Just for demonstration. Whatever. So addition, subtraction, really simple, really straightforward. Use a lot. It's important to note because even though that seems obvious, it always starts getting mixed up when you start learning dot products and cross products and stuff. But before I get into that, we'll talk about scalars. Scalars are super useful. Everything we do, I'm going to be normalizing, or neural networks or AI in general. So if you have a matrix with 1.7925 and your next data value is 1006 D, you want some way of having all of the data in here become something that you can put into any generalizable function and have it put out an output that's valuable to you. So the way you do this is to constrain everything to a value. Well, there's a couple ways of normalizing. You can normalize between minus 1 and 1, or you can normalize between 0 and 1. I always just normalize between 0 and 1 because it's really quick and easy to just mentally get percentages out of it. If 1 is 100% and 0 is 0%, then you know that 0.13 is the same thing as 13%, because percent literally means per 100, and per 100 literally means x divided by 100. So if my x is 13, 13 divided by 100 is 13%. 13 per 100. Sounds obvious and straightforward. Didn't make that connection while I was younger in high school learning this stuff, so I figured I'd just mention it. So the benefit to... Oops. Let's get rid of all this. The benefit to understanding this from a grounds up level is that knowing why you're doing the things that you're doing and not just following instructions because that's what a textbook tells you to do, makes a world of difference. So the textbooks are going to tell you to normalize your data. That way, the pre-built libraries that we're going to be using to train and save and process and evaluate models and stuff can just run off the same logic and the same algorithm over and over again. And to convert those values back into something that's more like your original data, to bring them back from those percentage values or the normalized values of nothing higher than 1, nothing greater than 1, you use a scalar. And the scalar is just going to be whatever you had to divide it by to get the normalized value. So what do I mean by that? Let's say I've got a list of high-ish numbers. All of these numbers are going to be greater than 1. So 67, 42, 25. One way of performing this normalization might be first to get the max value. And I'll just set that to a variable so I don't have to keep writing max value. And then 2, take that whole matrix, I'll just call this A, and divide it by Y. So you take all of these values, divide it by Y, and it gives me B, right? And then I do whatever I want to it afterwards, and if I want to convert it back after, all I have to do is take whatever this max value was that I divided everything by, and multiply it. So I could take B, multiply everything inside of it by Y, and I get back my original values. Very straightforward, very simple, but it's important to know what your system is doing. So just having seen this and noticed it, it's going to alleviate some confusion that you might have if you're just starting out and learning and you're coming across all these terms of, like, I don't want to say that they're complicated. It's just there's a mental load to having to translate things in your head that you're not familiar with. And when you start a project in something like AI, you're going to be covering statistics, you're going to be covering calculus, derivatives, like Navier-Stokes equations and fluid flows and things like that. We're going to be dealing with Blender, so it's like vertex groups and shaders, and then there's the material nodes, and you've got like lighting systems to worry about, and then they've got different input values for like the geometry or camera angles, or there's like lensing effects and things like that. So like every single piece of this, like all the instruments that we're using to be building this AI project, they're all going to have their own specific like industry-specific jargon and terminology, and a lot of them reuse the same words to mean different things. So like a vertex group in Blender, the 3D modeling software program, is just a grouping of different points that are shaped on a mesh. And a mesh is just like that object that we created out of the matrix, right? So instead of calling an object a matrix, they call it an object. But in our code, an object is going to be like a dictionary or an unordered list. In other words, it's going to be a list without indexes, that hash table. So we're going to be converting things from a hash table to a matrix to vertex groups, and all of these things kind of share the same words, but they mean different things. So it's really important to understand conceptually, like when you're working in one space versus another, what the term is meaning or intending to mean. And a good way of doing this is knowing what they're doing. Every time you come across it, if you take the time to stop and think about, like, what is this software implying, or what is it meaning, or what is it doing when it refers to a vertex group, as compared to what is my code doing when it refers to a two-dimensional n by m matrix. So that type of understanding is really important. Not the fact that you have to know all the math and the terminology, but as you use the software to understand what they mean by their terminologies, because it's not that they're wrong, it's a different space of knowledge, right? You're converting something from one language, and it might be an artifact in another language, but they're referring to different properties of the same structure, and they're implementing them and using them in different ways as instruments towards their stated purpose and goal. Like, the software's goal is not to run neural networks for me. The software's goal is to run my code for me. So I have to be very specific and say, I want this matrix to run a neural net. And in Blender, it's not even made to run artificial intelligence, but it does a whole bunch of matrices because it's measuring ray traces and lights casting from to and from and off of objects towards cameras and different sources and reflectivity and things like that, right? So they're working with the same types of math, and that's why I want to repurpose one into the other. But it's important to know that just because they use the same words, they're not necessarily referring intuitively to the same thing that you're thinking that it means to. Although it's not misuse of the word. It's just a different application. It's a different space for the word. So in geometric space, you might refer to a vertex group differently than you would in matrix space, or what do they call that? Hilbert space, I guess. I'm not sure. That was sort of the point I wanted to get to anyway. Scalars are important because that's how you're going to convert things back and forth from normalized values back to their original values. You're not going to use it too often, because usually once you normalize something and you plug it away, you can let the computers handle all the floating points. You don't really need it for yourself. But just in case, if you need to make sense of an output and you can't really tell what like a 16 or a 32-bit floating number is supposed to represent, it might help to be able to convert it back and forth. But again, at least knowing what the system is doing, that part's important, because if you just let things run away for themselves, there's not much you can engineer with respect to AI. You can copy instructions. Anybody can just follow a tutorial. But if you're trying to actually design and engineer and implement your own algorithm to do something that nobody else has done before, you kind of need to understand what it's doing. Even if you can't memorize or remember specifically the terminology for it, you just have to know what they imply when they say it. Do you know what I mean? So I'll get to the more complex stuff in another video. Because as I said, it's getting a bit late, and actually I was going to go over multiplication, but I'll do that in its own video too. Yeah, maybe tomorrow or tomorrow morning I'll do that. So matrix multiplication is a bit more complicated, and I'll just cover it quickly just so that we have some type of contrast between the addition and subtraction and the scalar multiplication that we already did. So first, you need, to do multiplication, you need two different shapes of vectors, or matrices or vectors, but doesn't really matter. So if I had 1, 2, 3, and 1, 2, 3. Yeah, so the number of m, n is your rows, m is your columns. This is the hardest part of dealing with matrices. Everything else is easy. This is the hardest part of dealing, in my opinion, because this is what always trips people up. This is what always causes complication and confusion. Anytime somebody, even PhD level, like I saw Yannick Kilcher do a video just the other day, and he was just off the top of his head trying to, he was thinking of something else and then just wanted to make sure he didn't blow by it. Everybody trips on this at some point, because you're trying to think ahead to something else, and this whole process is just inherently confusing, because it's not like the natural thing that you would normally do with numbers. But because essentially the way the output is calculated is by the n from the first matrix, from the A here, and the m from the second matrix, from the B here. So the output to this is a 1 by 1. In other words, it's a matrix with only one element in it. It's an array of only one element. So you started with 3 elements times 3 elements, and you end up with a 1. And that's because of the dimensionality of the actual shape of the matrices that we're multiplying together. And that's what makes them a lot more complicated too, is that the output values aren't necessarily the same as the input values unless you're doing square matrices. So typically what I would suggest, if at all possible, stick to 2 by 2 times 2 by 2, because then you know your output's always going to be a 2 by 2, right? Because it'll be the n and the M. So your output then becomes output 2 by 2, because it's the N of A and the M of B. That gives you your output. I'm going to cover this more in another video. I'm going to do actually a video just on row echelon form, because that's actually a really useful, it's a useful, I don't know what they call it, arithmetic or algebra or something like that. If you're trying to figure out things when you have multiple variables that are unknown, but you have like a known output. So for example, like if you were constantly going to the store and you have receipts, but you didn't know which items you were buying with those receipts, but you just had the total output and you were trying to figure out like what the values were for the items that you got. So you know which items you got, you know the total outcome, and you've gone to the store and gotten different orders several times, but you're not sure which value applies to which item. Like, okay, for example, like let's say you go to an art store and you're a painter, right? And you buy, you only buy 3 different types of items. You buy paintbrushes, paint, and canvases. But you only get a receipt for the total amount. But you know how many paintbrushes you bought, you know how much paint you bought, and you know how many canvases you bought. Well, shopping there once, you don't have any idea of the price for each individual item. But if you shop there a few times, you can cross-reference the different value outputs with the different amounts of items that you took home, and you can use matrix operations to figure out what the price is of each individual item. When you have multiple variables and one total output, you can use a really handy formula to figure this out. And it's not necessarily great or useful to be able to do it for yourself or on paper, but it's extremely useful to be able to tell a computer to do it, because computers scale very, very well. So you can apply that same formula and that same understanding, even though it's complicated and hard for us to do, even on hand and paper, right? Even for a simple example, like just with 3 items. But if you know the steps and the processes of how you would go about it, you can throw it into a library and the library will figure it out for you. And that type of operation is exactly what we're going to be using libraries for with our neural nets. Understanding how to do it the hard way, just once fundamentally how it's working, will let us scale that up like to incomprehensible sizes, even on home desktop computers, to figure out much more complex solutions to much more complex problems. And all you need to know is the basic foundation for it in one way. So as complicated as it seems, or as it may seem if you're not familiar with this type of stuff as I am, the utility to understanding it from the grounds up without all of the memorization and definitions and all that, of like the grassroots understanding for it, the utility of that is that you can apply it to scales that are like exponentially greater than you could ever do by hand with yourself. So learning how to process that type of problem-solving solution through code and understanding how to implement it in code requires that you understand the math behind it, at least fundamentally for the simplest example. Because if you know how to feed the algorithm the data it needs and structure it, and you can make sure you give it the right shapes, and you know which operations to put, is it a cross product or a dot product or a scalar value that you need to implement? Do I need to normalize this? What does it mean to normalize it? If you know those types of basic rudimentary foundational input constraints to the libraries and the algorithms that are already existing, you can then implement those tools in an unlimited other array of possibilities and apply them to different problems, like globally, not just for machine learning, but you can apply them to like house hunting or market analytics. Like you can actually apply it to anything from economics and purchases to like the way your country runs. You know what I mean? You can apply it to like city budgets and infrastructure spending or social services spending. And if you don't want to take it strictly through academics, you can apply it to linguistics models, and you can start building like translation AI services through symbolic tokens, as long as you know how to represent symbolic tokens through hash tables and data structures. And if you can maintain those shapes and, cross-reference them the way the libraries are built to handle them, you can then deconstruct them into meaningful outputs afterwards too. And it's not to say that you need to be able to do it all by hand. It's just to say that if you can do the simplest solution by hand, then it scales infinitely and Bob's your uncle. So I think that's enough for the intro to our math. I'll do another, as I said, a little bit more of a deep dive into the multiplication of matrices, because it's, as I said, it's really helpful to know this, the row echelon form, but mostly because I find anyway, all of the issues that I come across in just playing around and practicing and hacking around with neural networks, always, every time I get hit a stumbling block, it's always because of matrix multiplication. So I need the practice. So you're going to see more videos on it. And with that, stay tuned and thanks for watching.